Okay, so Phil, if you want to introduce yourself first, and then I'll go with my stuff, I guess.
Sure. Hello, everybody. Good evening. My name is Phil Savanowski. I think most of you know me, but for those of you that are joining online, I am a current mentor of Team 272, and I have been a mentor of Team 103 in the past. I'm also the head mentor of FTC 14133. My background, I am an engineer. I'm currently a systems engineer designing, who would have guessed, robotic systems that are used to automate mostly the food industry. I've been involved in FIRST for 15 plus years now, and I've generally used Onshape as my CAD platform. At work, I use SolidWorks. Welcome to the class. And Emily, if you would like to introduce yourself too.
Hi. Okay, sorry. Had trouble with my microphone. I'm Emily. I started with Team 272 when I was in 8th grade, and I started in FIRST when I was in 4th grade, and I just graduated. But I did Phil's CAD class a couple years ago in 2020, and I had done a little bit of more like less official CAD stuff with Phil before that. And during my time on robotics, I did a lot of stuff with the robot and specifically electronics. But it's very easy throughout the build season to see how important CAD is. So towards the end of this season, we got the idea to start the official class up again, and we kind of changed it around a little bit this year to try and make it very interactive for everyone. And yeah, so the first things that I want to go through are the things that were on the PDF that I sent out, just to make sure, like one last time, that we're all on the same page. So we'll be meeting every Monday and Wednesday night at 7 p.m. starting today and ending at on the last Wednesday of July. And all of the classes will be held over Google Meet, and I'll resend out the link every time we have a meeting, just so that you don't have to go searching through your email. And that email chain is going to be based off of who has filled out the Google form. So I'll update that depending on if more people have filled it out. But if you haven't filled it out, then I'm not going to have your email. So someone else can forward it to you. If you have anyone that you want to forward the link to, feel free to. But I'm only going to, after the first couple classes, I'm just going to be emailing the people on that list and not all of the mentors and stuff. And all of our CADing will be done on Onshape, so later on we'll go through making accounts and making sure that we're all in the same group, so that when Phil goes through different projects during meetings, we can watch along with him on our own accounts, or he'll be able to get into our projects through that. And so the class is set up with the first 3 to 4 weeks of the class will be learning how to CAD and going through the coursework and stuff like that. And then the last 2 weeks will be working with groups on your final projects, which is basically going to be designing robots to whatever level of detail you feel comfortable with. And these robots are going to be based around different game design challenges from the 2021 season. So we'll announce which games we're going to be using in a couple weeks, but so everyone's going to be getting to design robots with different kids on different teams for games that people have never designed robots for before. So we're very excited. Hopefully this will be a good class and we'll be able to do it again next year. If you miss a meeting and you want to rewatch it, they will most likely be posted to the 272 Cyber Crusaders YouTube channel. So you can go on there. I think we'll make them public, and if not, I'll be sending out the link if they're private. But if you have any questions about that, we'll let you know when they're posted, and you can just email the LC Robotics account. And during the class, I think it would be helpful for everyone to have like a piece of paper and a pencil to take notes down if you want, or you can take notes on your computer, because this is going to be learning stuff. And there is going to be like optional kind of outside of the class stuff that you can do. Onshape has a lot of like go through stuff yourself, kind of like self-taught classes that are very helpful with getting familiar with how everything is set up there. So that kind of stuff you'll be doing on your own, but you don't have to do it. It's not like mandatory or not graded or anything. And yeah, I think that's everything I had. So we'll make accounts for Onshape soon if you don't have one. But that was all of the introduction stuff that I had for the class.
Perfect. Thank you, Emily. Awesome. Emily went over just about everything. I'm going to start the class, but one more thing. The general format of the class is there's going to be some portion of kind of standard teaching lecture, what you might find in a normal class. The first portion is going to be primarily about CAD itself and designing things. The second portion is going to be about kind of different things and objects and maybe technical or engineering ideas as well as parts. So, for example, we're going to learn about bolts a little bit. We're going to learn about bearings a little bit. We're going to learn about gears, sprockets, that kind of thing throughout the class. And then the last portion of the class is going to be kind of in CAD or in the tutorial section or whatever, where we're actually doing stuff in CAD. And we might all be in the same document. We might be branching out into multiple groups and doing different things. So today my goal is to just get everybody into Onshape on their own account, set up, running, and maybe I'll make a quick document and we can all just go in there and just actually be in the same CAD space together, which, by the way, is something specifically unique to Onshape. It's the only CAD that I know of at this point that you can have multiple people working on the same document at the same time, which is really powerful. So I'm going to share my screen here and start the presentation. A lot of this stuff we've already gone over already. Can everybody see my screen? In a second, give it a second. All right, cool. Thank you, Hannah, for the thumbs up. Very helpful. So obviously this is our class. I did my introduction. So today our goal is to get access to all the course content, create an Onshape account and get into the system itself, introduce everybody to CAD and the Onshape interface, which is pretty universal between different CAD packages, but Onshape has a few of its own individual quirks. Get access to MKCAD, which is a library for FRC. We'll be talking more about that later. And then various other resources and things to look into and talk about. So we're going to start, everybody, start working through this portion of it. So this is going to require you to log into various different things, maybe create an account. So I suggest you can minimize the actual presentation here. As long as you can hear my voice, you can go through this. So for those of you that would like access to the CAD content, it's at this link, which obviously you guys can't click this link here, but I'm going to copy the link address and put it in the chat. It should be public, so please somebody click it and open it and let me know if it is public. And if not, I will make it public. I believe it's anybody with the link can view the stuff.
I got in.
Perfect. Awesome. So all of the course slideshows, all the content, like the stuff that I'm showing now, is going to be posted in this folder, as well as in the subfolder there is going to be the meeting recordings. I probably won't post, like none of the CAD files are going to be in here because those all exist in a similar system within Onshape. Onshape has its own file management system that's eerily similar to Google Drive. So is there anybody that has not gotten into the this coursework here? All right, perfect. Moving on. For those of you who have not created an Onshape account, how many people here do not have an Onshape account? All right, perfect. Let me see if I'm pronouncing that right. Is that one second, it went away from me. Adia. Am I pronouncing that
Oh, you
correctly?
can call me Addie.
Addie?
Yeah.
Okay, can you pronounce your whole name for me just so that I can know it?
It's Aditya.
Atia?
Aditya.
Aditya.
Yeah.
Perfect. Perfect. Awesome. So Adi and Aditya. Perfect. Nice to meet you. So to create an Onshape account, it's good that we have somebody that does not have an account. Most everybody does, so just be patient with us as we go through this. You're gonna go to this website that you see here, which is onshape.com/en, just means English, and /education. I'm going to copy the link and put it in the chat for us here, so you can just click on it to make life easier. And then I'm going to walk you through actually creating an account. So you should see this web page here. Let me know if you do, Addie.
Yeah, I did.
Perfect. So if you scroll down, you're going to see this section here where you just fill in a few tidbits of information about yourself, and you'll be able to create an education account. It's important that we use this portal to get into Onshape, because this creates a education specific account that kind of gives you a little bit more freedom and access to things you wouldn't normally have if you just created an Onshape account from scratch. And you don't have to pay for this as well.
Okay,
So let me know when you fill this out and you click the Create EDU button.
I did, yeah. I finished.
Perfect. It should ask you to confirm your email address next, I believe.
It says, tell us how you plan to use Onshape.
Oh, cool. Say there should be an option on there actually for robotics. You can put that on there as the answer. I should do this in like a incognito tab so that I could do it along with everybody.
So I have to enter my school website URL, city, state, country, graduation year, and what are you using Onshape for?
Perfect. Yeah. So fill all that information out. For your school, you could actually put Lansdale Catholic. I don't know which school specifically you go to, but maybe your school doesn't have this, but you can put Lansdale Catholic. It shouldn't really matter. I don't think they deny anybody if they go to a specific school. They're just trying to gather information, really.
Okay.
So let me know once you get past that. That's a pretty cool assembly. All right, Addie, how far are you along there?
I just need to enter a school website URL. So what should I put for
that? I think it's. Let me look it up.
It's just lansdalecatholic.com.
Oh, okay.
Or yeah. If you just Google Lansdale Catholic, it'll come up.
I'm gonna paste it into the chat here just so you have it. So you can just put that in there, all right?
Okay, thank you.
And no, this doesn't mean that you're signing up to be part of Lansdale Catholic or anything along those lines. It's purely, again, it's purely informational for Onshape's purpose. It's really for their advertising team.
All right, I got it.
Perfect. All right, where are you at now?
Activation email.
Yep. Good. So now you're going to go into your email account that you signed up for the account with. You're just going to click on the link in the email, just like most other account creation services do.
All right. All right, I just have to create my password. That looks good.
Cool. create your password.
All right, I got it created.
All right, perfect. Sounds good. Just make sure you can log into it, but otherwise I'm going to keep moving on. All right.
All right, thank you.
Yep. All right. So after we've created an Onshape account, next is getting access to this specific class's Onshape team. So for those of you who have done CAD classes and stuff with me before, we're actually going to be using the same team. So if you're there, you're probably already on the team. But if not, I'm going to need your email address. And if you could just post that in the chat, I can add you to, it's a group called CAD Curriculum. I think it looks like it's actually owned by Joe. Interesting. I thought I created it. Perfect. So I'm just going to go quickly and add these people who are posting in here. Some of you, again, probably already are in this, but I'm just going to add you anyway. I shouldn't double add. Chabrias. I see the Chabrias have a very specific way of doing their emails. Did your parents help you make your emails for the first time? My mom helped me with mine, like not naming it something ridiculous or that I would forget. Sihan, what's up?
I'm on the page where it's asking me to set the default units and what units are we gonna use?
We're generally going to be using inch, and that's only because most of the components and standards that we use in FRC are in inch. I am a metric fanboy and will always be a metric fanboy. It is the superior system. Don't let anybody tell you otherwise. But we use the imperial system just because everybody else uses it, which is a bad reason, but it's a reason. Okay?
And degrees, or are we going to use degrees or radian?
Generally degrees.
And pound for wood?
And pounds, yes.
Okay, thank you.
And you can switch between these like throughout. Like that, when you don't just select that and it's just that's the only option that you have. You'll be able to switch between them at a later point in time.
Okay, thank you.
All right. So if everybody's logged into Onshape, and if you just refresh kind of the home Onshape page here, I've added everybody that posted their email into the chat here. You should see on the left side a thing that says Teams. And if you drop down the Teams, you should see one that says CAD Curriculum. Can everybody confirm or let me know if you don't see that CAD Curriculum tab?
I'm in.
All right, perfect.
I do not see it.
Who was that just speaking?
Ryan Stumpf.
Right.
Maybe try refreshing the page.
Yeah.
So it. Okay.
Did you say it's there now?
No, it's not.
All right.
Oh wait, I put the wrong email in. That's why.
I was going to say, make sure the email that you texted in here is the one that is created with your Onshape account, or the one you created for your Onshape account. There we go. All right. Should have that now.
Yep, got it.
Perfect. All right. So there's not much in here now except for stuff from previous classes. And anybody, all of you, you're more than welcome to go in here and poke around and look at the different things we did. Arguably, the coolest thing that we have is this Robots to the Rescue document. So if you would like, on your own time or whatever, I might open it actually for some examples and details on like assemblies and sketches and stuff like that. It's a really good, cool reference document. But that's a really, really cool model. There was a design challenge 2 years ago where where Onshape basically hosted a competition to create a robot that solves a problem. And we created a robot that took packages and delivered them to people in their own homes to prevent them from contracting COVID or just needing to leave their home to get packages and stuff. Pretty cool. We'll look at that some other time, but I'm going to keep moving forward here. Cool. So everybody's in Onshape and has access to the course content in Google. So I'm going to keep talking here, and now I'm going to start talking specifically about parametric modeling. So let's back up a little bit maybe and talk about CAD. CAD stands for computer-aided design. There's a lot of different forms of CAD out there, and they don't necessarily always have to be designing a like a part or some physical object. For example, a lot of CAD could be for animation, or could be for you know, rendering cool images of things, not for any practical purpose, but just for artwork. You could have CAD that's artwork. There's various 2D CAD platforms. There's various 3D CAD platforms. Onshape is generally considered a 3D CAD platform. You can do 2D stuff in there, but it's built around generating 3D objects. So within CAD, there is parametric CAD and there's non-parametric CAD. Non-parametric CAD is like before computers existed, people actually used to draw all the things that they draw today on a computer on a big sheet of paper on what's called a drafting table. This really fancy table that had these cool rulers and stuff that moved all around the table. And non-parametric CAD would be if you drew something on paper and then you needed to, let's say you made something 10 inches, but then you figured out later that instead it needed to be 12 inches. Well, what do you need to do if you draw it on paper? You need to erase at least a portion of the thing and start over to make it 10 inches. Now, or 12 inches. Now, what happened if you drew something else at that 10-inch point that needed to also move with the addition of those 2 inches? You'd have to erase all of that stuff as well and start over in a new place. So that would be non-parametric or basic CAD. And most 2D software is generally like that. So maybe you've heard of a program called AutoCAD. AutoCAD is very much kind of in that mindset. It has a little bit more powerful tools than just straight up sketching on a piece of paper, where you can create like a block that you can copy and paste into a bunch of different places. Then you can edit that block. And now anywhere that block exists, it will change to be whatever you edited it to. But you still run into the issue where if you wanted to put something at 10 inches away or 12 inches away when it's currently at 10 inches, it won't automatically move that 10 inches. So that's where parametric modeling comes into play. Now, parametric modeling means modeling or designing with specific parameters that can be changed at any point. And I like to use the analogy or the metaphor of it's like building a house of cards and being able to, at any point in time throughout, you could be halfway done, you could be, the house of cards could be fully built, but at any point in time, pausing time, pulling out the very bottom card and replacing it with a different card, and having the whole house of cards stay together without falling. Obviously, that's impossible in a real world scenario, but I like to use the analogy as well that in CAD, in parametric modeling, we are time travelers. We have the ability to go back in time to when different features were created. And we have the ability not even to just travel time, but also manipulate time and change when certain features were created and what they're related to or what they're not related to. It's very powerful. It's very confusing at first, but we're going to try to get everybody to understand it a little bit. I'm not going to go through all that today. For future classes, we're going to get to the basic stuff, but that's kind of where CAD and parametric modeling is really, really powerful. When you're able to utilize that functionality of it, it makes making wide sweeping changes to the design of something so much easier. Perfect. Another important thing about parametric modeling is that the order in which something is done, the order in which you add features and stuff is very important. Compare that to to drawing on a piece of paper. The order in which you draw on a piece of paper doesn't really matter. Maybe you start with like the upper right corner of a piece of art, and then you go to the bottom left corner, then you go to the center, and then you have to at some point in the future make a change to the upper right corner. You can erase that and go back. But the order doesn't particularly matter in that form, which is the analogy to 2D CAD and AutoCAD. But in parametric CAD, the order really matters because we're building things on top of each other and making modifications to things that exist already, that you're using that geometry to reference as reference. We'll talk about that a bit later. All right, moving on. Most of the parts, believe it or not, most of the parts that you will design for really anything in your life, if we're talking about designing machinery and designing things, physical things, they already exist. They're out there. They've been modeled. They have weights to them. They might have like colors and other crazy things that they have. We don't need to CAD every single part of the robot. Now, back when I was your age and when I was learning CAD, I needed to CAD every single part of the robot. There wasn't these giant libraries of parts that existed. Each team kind of made their own little library of parts. And we didn't have, websites capable of hosting thousands of gigabytes worth of data of CAD files, nor online CAD systems. So consider yourself lucky. But now there exist these things that are called libraries. They also exist in programming, if you're familiar with the idea of programming of libraries, where it's a collection of contents. In the case of CAD, it's usually parts that have different parameters. They're all totally built and they're to the spec of the part. They have materials a lot of times. Basically, they're parts that already exist that you have in CAD that all you need to do is find them and then you can pull them into your assembly. And I'm saying that because I want to make sure that somebody doesn't go and try to design like every single screw that needs to be designed for their robot. Screws are standard parts that already exist in libraries that we'll be able to utilize very quickly through a library. We won't have to design every single one of them. That's just one example, but it goes to bearings, to wheels, to frame structure materials, to motors, to sensors, to electronics, to all kinds of different stuff. And we're going to go through and we're going to use a lot of those materials, a lot of those library components. And what I'm going to focus on with everybody is utilizing those library components, but primarily designing the parts that aren't in the libraries, because that's really what each individual robotics team and people that aren't just designing robots, but people that are designing things in the real world, they don't design the stuff that already exists. They design the new, unique, custom parts, and that's what we're going to focus on here as well. The library that we're going to be using here primarily is going to be called MKCAD. It's developed by a team called the Milken Knights, and they're from California. They just had a huge library that they were making in Onshape already, and they decided, hey, well, why don't we make this available to everybody? And now there's a whole group of people that are a part of that team that help support it and add content to it. I'm actually one of those people. I've added probably 150 or so things to MKCAD, from bearings and wheels and new components that these suppliers release and stuff like that, and assemblies. And there's plenty of other websites as well where you can get CAD content from. You can go to OEM. OEM stands for Original Equipment Manufacturers. You can go to the OEM websites. So, for example, Andy Mark has CAD of every single one of its components. Rev has CAD for every single one of its components, and Vex, same thing. And there's plenty other companies out here that do supply their own CAD. Another good example that I didn't list here is Bimba. It's a company that makes air cylinders, you know, like the extend, retract cylinders that you see on robots everywhere. You can go in there and plug in a few numbers, and it'll actually generate a custom cylinder for you if you like, of any stroke, of any diameter, of any rod end type. So there's tools out there that we're going to try to use. And then there's also tons of catalog websites out there that supply CAD for parts as well. My favorite is probably McMaster, and we're actually going to go into McMaster and get a little bit familiar with it today, because in the future we're going to be using McMaster to find parts and also generate like CAD for them and bring the CAD into Onshape. Granger, which is similar to McMaster, and then probably my most uniquely favorite one is Masumi, which is a relatively new site, and they make all kinds of custom pieces that you can customize on their websites through their configurators. There's lots of others. Those are just the ones that I'm going to utilize today and throughout this class. But long story short, and the general message that I'm trying to convey is only CAD what doesn't exist. Do not CAD the things that already exist and are already designed. You want to focus your skills, your attention, your focus on the new, custom, unique parts. All right, moving on. These are a few just little examples of parts, and the way the CAD generally works is you will create a sketch that you make a feature from, and whenever you make a 2D sketch into something 3D, that creates a part, and then you're going to take that part and other parts that you've made or other parts that exist in libraries and bring them together in an assembly and assemble them. And that's how all of CAD is done currently, and likely will be for some time. So here I just have a few of these images here just to show that this over here on the left is known as the feature tree, and this is showing you all the different components of this part, all the different things that were done to create this part that you see. And same thing over here. This is just a part that I designed. All right. So we're going to talk about features. I mentioned sketches already. Sketches are 2D profiles, and we're going to talk more about them next class primarily. But I want to talk about features a little bit specifically. Features are modifications or additions that you make to objects in CAD. Almost all of the features, all the major features that we're going to use, start with some kind of a sketch. So you make a sketch that describes the kind of general shape of something maybe, and then you'll use that sketch to make a feature which brings the 2D sketch into 3D. And examples of this are extrude, revolve, sweep, loft, and hull. We're going to go through all these in detail later in the class. And then there's some other features that don't require sketches and that just edit the geometry that already exists. Those, for example, are radius and chamfer, draft and thicken. There's a bunch of others as well. And as I talked about before with the parametric, these features contain parameters. They contain values that can be edited and changed to give you the shape and the geometry of the parts that you desire. And these parameters are going to be kind of the more important parts of your system, and how you relate these parameters to each other are going to be pretty critical. And I wanted to bring up one more specific thing about Onshape. And for those of you not so familiar with CAD, this might not make a whole lot of sense just yet. But Onshape uses something called Part Studio modeling. So in most other CAD software, you have a one part is one file. So there's a one-to-one there, and that means you have to have unique files and unique sketches for every part. And that's how it's been done for a very long time. Well, Onshape kind of came onto the market, and they do this thing called Part Studio. And at a high level, all that means is you can make multiple parts in one file. And they just call them studios because they don't really have files. They have like these big folder things. But it's useful because you could then use one sketch or one feature to affect multiple parts. The example that I use is, say you have a plate that has like 3 different holes in it in different locations. And that plate needs to line up with a block, which needs to line up with like a base plate as well. So there's like 3 parts here, and they all have these holes going through them. In traditional CAD, in SolidWorks or in some others, you would need, if you wanted to change the position of any one of those holes, you would need to open up each individual part and change the position of that hole to the new position. Well, in Onshape, if you make a feature that goes through all those parts at once, you only need to change a position of that hole once, and it changes it in all 3 parts at once at the same time. Super useful. This is the future of where CAD's going, and where companies are like, oh, why didn't we do that before? Because it's so much more capable. It allows you to better able to relate parts to each other, and it's just easier to manipulate stuff with these part studios. They can get kind of big and complex and ugly. So there are certain times where you want to split things up into like this part studio versus this part studio. Like I wouldn't necessarily design one robot, one like FRC level robot in one single part studio. We probably want to break it up into like subsystems at least. But part studios are awesome. Let's see. As I mentioned, a single feature can affect multiple parts, which is generally a good thing. So if you want to stick a hole through something altogether, if you wanted to add like a bar that goes through all the parts, you can do that all with one feature. And you can also use one sketch to create multiple features. So we're going to do this. We're going to learn how to do this. And that's going to be layout sketches. It's how to create a sketch that gives you the very high level positions of things that you can reference for other portions of the design. So I know I'm talking pretty high level, and this might not make a lot of sense to everybody. We're going to get into this in more detail. Just bear with me. And please, at any point in time, if you have a question, just use the little hand raise thingy, or just stop me and interrupt me. How's everybody doing so far? Good? All right, cool. I put in this note again as well. Do not model standard components. Those things already exist in life. We've talked about this before. Do not model standard components. I'm going to talk about some general best modeling and CAD practices. You almost always want to center your parts or your sketches, your first new sketches on a new part on the origin. And I'll talk about what the origin means. The origin is there's 3 planes that intersect that create this one single point. The X plane, the Y plane, and the Z plane. Or the top, front, and right planes. And you always want to try to center your part on that origin. There's obviously exceptions to this. Like, for example, when we design robots, we don't center the robot on the origin. We center it on the origin from the top looking down, but we actually put it on the top plane. In other words, we design it as if it's sitting on the floor. It's like we have the wheels touching the floor in the design, and that allows us to realistically calculate the center of gravity and how high the center of gravity is from the robot. That's an important thing in robots and many other aspects as well. You generally only want to model one instance of any part. What's a good example of this? Cars, right? Cars have 4 wheels, for example, right? But all 4 of those wheels are identical to each other. So when you're designing something in CAD and in your part studios, you generally only want to make one of anything that is being used multiple times in the assembly. So I use the example of tires, but in robotics, this could be like your frame plates or pieces or crossbars. If you have one crossbar length that's used 10 times over, only design it once and reuse that same piece over multiple times. Not only does this decrease like the load time of the model, it makes it so that if you make a change to that single part, it will carry that change through everywhere that it's used in the assembly. Sometimes you want to do that, sometimes you don't want to do that, but it's easier to replace the part with a new one than it is to like have 10 different parts that you want to change all the features of at once. And they're all unique parts. We generally want to minimize the feature tree. And the feature tree, like I said, it's that little thing over here on the left. Our goal is going to be to make the part that we want to make with as few of those features as reasonably possible. Now, you still want to have a good number so that you can edit certain things and get to where you want to go. But generally, the fewer of them that you have, the easier it is to manipulate your model. You have less searching for features, and it makes your assembly more legible to other people. Oh, one thing I did mention, at a high level, CAD is a communication tool. It's used to communicate design and design intent to people. And those are 2 unique things. So if somebody takes the drawings that we make out of CAD and they just look at the drawing and they say, okay, this is this tolerance and this tolerance, and they don't know like what this part mates up to, and they don't know where it fits or anything like that. They're just going to make it to exactly what you specify, but maybe what you specified was wrong. So that's where having the whole model and in context, it helps you better able to specify the design intent of your design, to say what you wanted to design, because what you design isn't always what you want to design. All right, cool. Moving on. We're going to talk about generally where we should start parts. I mentioned always starting it on the origin. So I've got a few objects on the screen here, and I would like somebody to answer. And there's no specifically right or wrong answer, but I would like somebody to answer of where they think they should start each of these parts. So on the bottom here, we have a table. On the right, we have a hammer, a little custom machined hammer. And then on the top, these are called V blocks. These are used in manufacturing machining. And you put a round object in this V here, and it keeps it nice and centered across the width of the block. So, all right, who's got an idea of where the table should be started relating to the 3 planes? Maybe let me open up Onshape. to explain the 3 planes for a second. I'm just gonna make a new document. Anybody? Whoever just raised their hand.
It would be on the top plane.
Perfect. So, well, you figured out what would be on the top plane.
Sorry, the table.
What part of the table will be on the top plane? Will the top of the table be on the top plane?
The legs of the table.
Good. Very good. This kind of goes in. Do you remember that demo that I do with the peanut butter and jelly, with telling people precisely what you want them to do, right?
Yeah.
The same thing goes in CAD. You have to be very explicit when you're talking about things. So good. So you generally would want the legs on the bottom of the table, kind of similar to how we would design a robot, starting on the top plane and going up from there. What about the rest of the table? What about from left to right or front to back? Bihan, I'm gonna pick on you again.
I guess the middle of the table, like yeah, the middle of the table should on the legs. You should put it on the origin.
Perfect. So left to right in the middle, right?
Yeah.
And front to back in the middle. Good. I think that seems like a reasonable place. Yeah. Awesome. Perfect. All right. How about this hammer? Somebody that is not named Vihan. This one's a little bit more complicated for sure. And again, there is no explicit right answer. There's generally good practices, but you could say, I'm going to start it out 100 meters away from the origin, and that would you technically could, and there would be nothing objectively wrong with that. It would just be more difficult for other people to use. So where do we think this hammer should start? Make it a little bit bigger. Maybe it's too small for people. Emily.
I feel like the bottom part of the handle, like having it stand upright, that should be where the bottom of the, like where the origin is centered on there.
Perfect. So something like, it's obviously not the right perspective, but something like this?
Yeah, kind of. And then the like long part of the actual hammer will be kind of like on the Z axis, I guess, like going towards you.
Cool. Perfect. And then one of these faces would be front facing and one of them would be right facing, right?
Yeah.
Perfect. Yep. I'd say that's a reasonable way to do it. Absolutely. I think you could also reasonably do it on the side like this, where this is the origin and then you sketch it along to the side, or you could do it upside down so that this side's at the origin and this is further away from the origin. Generally, I'd say I think Emily's option was probably the best of the 3 that I just pointed out, but yep, exactly. All right, how about this part? Anybody else that isn't Fihan or Emily? Make these a little bigger. Does anybody have a question about what these are? I'm going to search this up just that people. So I'm going to see if I can find one being used. Like this. Can everybody see that? So they're used to hold like round pieces, generally speaking. And the important part is that it centers the round piece from left to right on the block. Like I said, these are used in manufacturing and part holding. There's another good drawing of it. So any idea where this should start in terms of the planes? Thoughts? Sihan.
Would it be the bottom of the block on the top top side.
I think that seems reasonable. Cool. So the bottom of the block on the top. Okay, what about the other directions?
I guess like this, you see this flat side that's on the, yeah, this side you're pointing at should be like either the X or Z axis.
The X or Z is generally up.
Oh, well, then X and Y then.
Cool, perfect. So it's good you guys are already familiar with X and Y. So a lot of CAD is in, that's known as the Cartesian coordinate plane, right? And I'm using my right hand here. I don't know if everybody's used the right hand rule. If you put your hands like this, where you're pointing your finger forward, pointing your middle finger at 90 degrees to that, and if you point your thumb up, that will generate your XYZ axis. So that's good to know. And then your top plane is your X and Y. Your front plane is your Y and Z. And your right plane is your X and your Z. I think Onshape actually shows that. Yeah. Look up here, right? Up on the top right in this corner. So Z is in the direction of the top plane. X is in the direction of the right plane, but it contains the front and the top plane. And Y is in the direction of the front plane. That makes sense? Cool, cool. Awesome. Good stuff. One other option that I might suggest to this one is, and this is kind of like a trick question. So do you see how these V blocks use these round parts, right? Maybe we want the origin to be centered on the round instead. So instead of the top being the very bottom of our block, the top could maybe go right through the center of the thing. Maybe, maybe not. The problem is in that scenario, so I take that back. You don't know what round piece you're putting in the V block. It could be different diameters, and that would put you at different heights. So I think, Sihan, I think you got it correct. Good stuff. All right. Moving on. Here's the other important thing about starting and designing parts is you want to start your part with a sketch that defines as much geometry of the part as possible. That's usually the case. That's not always the case. Sometimes you want to start with a simpler side of the part and then make more difficult geometry later. But most of the time you want to do that. So for example, what might we sketch first on this part? Would we sketch it from this side? Would we sketch it from this side? Anybody? Vihan.
You would sketch it from the front side.
And why is that?
Because all throughout it just extends itself.
Good, very good. This is known as like an extrusion, is what we would call this. So this profile is the same all the way through this part. So by starting your sketch on this side, you have one sketch and one extrusion that makes the whole shape of the part, basically, except for the crossbar piece. Compared to if you drew it from the side here, you'd make a rectangle, and then you have to come back to this front and cut out these other profiles, and that would be two features instead of just one feature. Perfect. Good, good. All right. Moving on. I wanted to use this time to talk about some other resources that exist out there that I think you guys should know about and that you should try to utilize. The main one that I'm going to point out probably is Chief Delphi, which is an online forum for FIRST Robotics specifically. There's all kinds of content that goes on there. The Blue Alliance is a website that has videos of matches for robotics and information about different events. There's a Discord for FIRST, and there's also, I believe, Discord for each different level and each different region of FIRST. So that exists if you would like to join that. This is a engineering calculator that was created by a mentor of one of the best teams in FIRST right now. And then we're going to be, in the future, we're going to be talking about chains and belts a little bit, which are different ways to transmit torque and power. These are calculators that allow you to measure the distance, or calculate the distance between where one shaft of a chain would be and where another shaft of a chain would be. And then there's tons of other different physics and engineering calculators online if you just search for it. Tons and tons of other stuff out there. And then Engineering Toolbox is a good place that I go to for like general stuff. They have all these kinds of tools on the left, from fluid mechanics to physical mechanics, statics, thermodynamics, electrical dynamics, lots and lots of tools. So here's an acceleration calculator and a page that explains what acceleration is. So if you're more interested in engineering stuff, this is a great website to come in and just poke around and see what they've got going on. Hundreds of times in my career, I've come to this website through just like a Google search, and I'm like, man, I should just use that as a starting point instead. Awesome. All right, on this next page is where I want to spend most of the rest of the day, the class with everybody, as well as in Onshape proper. Actually, should I do that first? Sorry, I'm gonna back up a little bit, and we're gonna go to McMaster. So McMaster was one of the websites. If you're already on the tutorials page, that's fine. Just leave it open. But McMaster was one of those sites that I suggested in the parts that already exist. McMaster is essentially a giant catalog of parts. So I have no idea how many individual parts there are in this website. Immense, probably too many for any individual to count, but probably on the upwards of like a billion, close to a billion. It's got tons and tons of things. This is kind of usually my first place to go to for parts and components of things if I couldn't find them on one of the existing libraries. And all you need to do in McMaster is look up what kind of part that you want. So maybe I want a bearing. Search up bearings. Wow, look at how many options for bearings we have. There's like 20 of them. Well, I think I'm pretty sure I want a ball bearing. That's the kind of bearing that I want. Wow, even within ball bearings, there's like 15 different options of ball bearings. So you have to go and continuously kind of narrow down your search. So maybe I don't know what type of bearing I want. Let's get away from the bearing. Well, on the left side here, you can specify some dimensions for your bearings, right? And what kind of bearing you want to have. So I'm going to use a bearing that has a flange on it. And what do I mean by flange? So here is what a flange bearing looks like. It has this extra like lip on it. And that lip is to prevent the bearing from like going through the hole. It basically gets pushed into a hole and it can't go any further into the hole because of that flange. All right. Compare that to this it's kind of a flange bearing. Let's see if I can find it. Here's a good cross section of a flanged bearing. Just give you a better idea. And then if you just look up regular Bearing cross section. Here's what a regular bearing looks like. It doesn't have that flange on it. So these can be pushed in and they can go across or through a hole pretty far. They usually have some kind of backing surface that prevents them from getting pushed out of a hole. So, all right, let's come to this McMaster page. And we're looking at all these bearings. We're overwhelmed. These are too many bearings. Well, we know that we want to use a 1/2-inch shaft for this bearing. Maybe that's the information that we'd know. And let's say we do want a flanged bearing. And maybe it's not important that our bearing's sealed. Like the balls can be exposed to the atmosphere. We don't have to worry about like dirt and grime getting in there. So we're gonna have open bearings. And let's say we don't want an extended bearing. We want it to just be a flat, thin bearing. And look at that. In a few clicks of a button, we went from millions and millions of options to literally 2 individual unique options. And maybe these aren't quite the right ones that we want, but you get the idea where we're able to really, really quickly narrow down our search for things. Maybe I don't want these plastic ball bearings. So if I take that off, and if I take off, let's see what else. Flange. Oh, look, now we have all these other options for bearings that exist. Perfect. So that's the general gist of McMaster. Come here for any kind of mechanical component that you don't find in your libraries. Shaft collars are a common thing that I come here for. You can have these kinds of shaft collars, these kinds of shaft collars, these kinds of shaft collars. Maybe you want 2-piece ones. Maybe you want hinged ones. That's pretty cool, actually. I've never seen one of those. But generally, you get the idea. It's a really great place. And the cool thing about McMaster is each one of these parts in here, you click on the individual part number, you click product details, has a detailed drawing that you see. And then over here on the right, you can download the CAD of the part. So these are the kind of parts that I'm talking about where if this is the part that you need, you don't want to model it because it already exists. And the time that it takes to draw this is better spent on parts that don't exist already. So let's say this is the exact part that we want. We can come into here and we can hit download. It downloads it onto your computer. And then in Onshape, there's a whole button here under Create called Import. We'll go into that in the future, but I more so wanted to show everybody McMaster and start to get familiar with it. So let me do this. I'm gonna do a little live test with everybody. Does everybody have McMaster car open right now? Does anybody not have McMaster car open right now? All right, cool. I'm gonna tell you guys the details of a part, and I want you to tell me what part number it is. Okay. Now again, there's millions of things in here, so it seems like it's a complicated thing, but as long as I give you the right specifications, you should be able to find it. I'm gonna do a pin. I'm gonna do a dowel pin. It's gonna be there. It's gonna be that. It's gonna be that. It's gonna be this long. And it's gonna be this type. All right. So the first person to tell me the part number of this part, I don't know, you get a gold star. So does everybody have McMaster open? Cool. Perfect.
Just a minute.
Sure. Take your time. Take your time.
All right, I got it.
All right. So you are going to be looking for a dowel pin. Something called a dowel pin. D-O-W-E-L. it's a metal pin that they're usually like pretty precise in diameter. So your first step should be to just type into the search in McMaster dowel pin, D-O-W-E-L, or just pin. If you just type in pin, dowel pins will show up. So once you get there, the dowel pin, whose number I'm looking for, has a diameter of 1/4 of an inch, has a length of 1.5 inches. It has a chamfered end, and it is made of 18-8 stainless steel. Those should be all the specifications that you need to find this very specific dowel pin that I'm referencing. If you have the number, if you figured out the number for that dowel pin, feel free to unmute and say what the number is, and I'll tell you if you're right. I'll go through this. Oh, are you ready already?
No. What's the length?
Sure. I'm going to go through the whole specifications again, okay?
Thanks.
It's 1/4 of an inch in diameter. It's 1.5 inches long, and it is made of 18-8 stainless steel, and it has a chamfered end. So again, if you figured out what the number is, just let me know. One more time. The diameter is 1/4 of an inch. It's a dowel pin, D-O-W-E-L. The diameter is 1/4 of an inch. The length is 1.5 inches. The material is 18-8 stainless steel. And the end is chamfered. Has anybody found the right part yet?
I mean, I have 4 options. I don't know which one it is.
Okay. You have 4 options. See if you can narrow those 4 options down. You should only have, if you've selected all those things that I selected, you should only be left with 1 option. I'll say them one more time before I call on Hannah. And then I'm going to call on Hannah. So it's a dowel pin. It is 1/4 of an inch in diameter. It is 1.5 inches in length. It is made of 18-8 stainless steel, which is just a specific type of stainless steel. And it has a chamfered end. All right. Hannah.
All right, I kind of feel like I'm cheating because I use McMaster on a daily basis. But is it 90145A546?
Yep. That's it. Did anybody else get that number? Is anybody else able to find that number?
I got it.
Perfect.
Yes.
All right. All right, good. Cool. I want everybody to be able to find that number. So everybody go through this. This is an exercise in learning how to use a tool. And that's really what McMaster is to us. It's a tool to find parts that already exist out in the world that we can get cheaply and quickly for our robots and for all kinds of other things as well. Turn on some light. It is dark in here. Has anybody not been able to find that part yet? Sihan, have you been able to find it?
I think I have it, but there's like a list of I do have like all the filters on, but there are 7 options here for me.
Okay. Do you have only stainless steel selected?
Yeah, I have 18-8 stainless steel.
Okay. What other options do you have selected on the left?
0.25 diameter, 1.5 length, chamfered end shape, and pin type is down.
Might be your pin type, because I don't have pin type dowel selected.
I just unselected that, and there's more options now.
Okay, let's see why that's the case real quick, because I don't want to give you guys an example that doesn't lead you down to the one single part. So let's see. Oh, you know what it might be? In diameter. No, that looks like it's right. In diameter, you do have 1/4, right? Like 1/4.
Oh, I have 0.25.
Okay. For some reason, yours is saying 0.25. I don't have a 0.25 option.
I'll put 1.
Yeah,
I'll
look.
put 1.
Oh, did you type it in?
Yeah, I typed in.
Okay, don't type it in.
0.25.
Don't type it
Oh.
in. Try to click on the options that you have there. You could type it in, but
Oh.
I generally just click the options that I see there.
Oh. Yeah.
So you just have to scroll down until you find the right options.
So 1/4
Yep.
inch for diameter, 1.5 inch for length.
Yep.
18-8 stainless steel and chamfered end shape.
Yep. Which one did you come up with?
I have 11 options.
11 options.
Yeah, the first one says dowel pins. Oh wait, it might. Is it 90145A546?
Yes, sir. Yes, it is. That's the one. What are the other ones? What do they say? Not the numbers, but like what kind?
Oversized dowel pins, pull-out dowel pins, flat vent pull-out dowel pins, spiral vent pull-out.
Got it. So what I didn't specify, what I should have said was that we're just looking for dowel pins, standard dowel pins, because that's the one other selector that would have brought you to that one part. So my bad on that. But cool, we found a dowel pin. I'm going to do this one more time, and I'm going to try to be more specific with my selection so we can get more familiar with this. What's another common thing that's used in robotics here that we get from McMaster? I'm going to do bolts because that's a pretty common thing. I'm going to use my favorite kind of screws. They're called shoulder bolts or shoulder screws. So if you look up shoulder screws, let's see, steel, socket, let's go 1/2 inch, and let's see. All right. So if you look up shoulder screws, there's a whole bunch of different types of shoulder screws. If you look up alloy shoulder screws, I'm looking for a shoulder screw of a diameter that is 3/8 of an inch, and the length of which is 1/2 of an inch. The thread size, which is 1/4-20. We'll explain what that is in a future lesson, what that means. 1/4-20. It's steel. It's a steel shoulder bolt. And it has a socket head type. It should call out alloy steel precision shoulder screw. So if you have multiple options, that should be the one that it's under. If anybody has the number that isn't Hannah, please state the number. So I'll say the specifications one more time. It's an alloy steel precision shoulder screw. The shoulder diameter is 3/8 of an inch. That is 3/8. The shoulder length is 1/2 of an inch. The thread size is 1/4 of an inch -20. The material is steel. And the head type is a socket. Socket head type. Does anybody have the part number? Ella?
I'm not 100% sure, but I think it's 92012A309.
That is the part that I was looking at. Exactly.
Nice.
Precisely. So I want everybody while they're on that page, just so they can get familiar with this. You can either download the CAD right from here, where you see there's a drop down. All right, I'm going to come and pull this back over here so everybody can see my screen. So there's a drop down where you can choose what file format you want. Generally, we'll use SolidWorks or Step. Those are the two common options. And then you hit the download button, and it will just download to your computer. For whatever reason, mine didn't work. But I also want everybody to go into product details and to see, you know, the CAD drawing of it and all the other very, very specific detailed information about this screw. Got all kinds of specifics. Got the specific material. It's got how hard it is. It's got how strong it is. It's got the type of thread, the drive size, so how big of a hex shaft you need, or a hex, like an Allen wrench you need. All these details, so many of which probably aren't even relevant to what we do, but it's all there. The tolerance of the shoulder, which is actually important. These are my favorite bolts because they're made to fit bearings. They have a very precise tolerance on the shoulder diameter. And so that's used to fit bearings. You can take a bearing and put it on one of these bolts and then bolt the bolt into something, and then you have a shaft that's automatically there. Super easy. Cool. All right. Any questions? All right, cool. We will be using McMaster in this class for some stuff. So, and you will likely be using it in your life if you do any kind of thing in any field that makes stuff. You will be using McMaster. I can almost guarantee. All right, moving forward. Let's jump into the Onshape tutorial area. This is where I'm gonna have a suggested tutorial to take before each class, essentially, multiple maybe. These are self-guided, self-paced tutorials that you can watch. There's also plenty of videos like on YouTube or whatever that you could watch people doing this stuff. And I'm going to go over a lot of it in the next class, but it's helpful to have kind of the professional take on it first from like actual people that know how to teach, unlike me. So I would like everybody to go to learn.onshape.com when they're logged into their account. And this kind of crazy page should show up. And when you're in this page, we're going to go into, there's a few ways to get there, but there's these self-paced courses. You can do there, or you can just click it, scroll down a little bit. It's right here, self-paced courses. So I'm going to click on self-paced courses there. And there's a whole lot of different options here. So within self-paced courses, I'm going to look at CAD basics. All these would be good ones to do. But the ones that I'm suggesting for today's class in preparation for Wednesday's class is, what am I suggesting? Navigating Onshape and Introduction to Sketching. So you'll see those two are right here, Navigating Onshape and Introduction to Sketching. I would probably do Navigating Onshape first, just so you can kind of get yourself familiar with how Onshape is set up. So all you need to do for these is, it's a series of videos that you just watch and click through, and they have extra resources for you on the left here. And you just go at your own pace. You watch them, go to the next lesson. You can skip things if they seem irrelevant. And then they've got little like questionnaires where you can answer the questions. And so in Onshape, this answer is false. I think I got that right. Which direction should you box select to ensure you only select everything fully contained in the box? That would be right to left. I only know these things because I've been CADing for forever. To deselect, oh, I don't even know this one. Maybe escape. Oh, I only got one question right. I clearly need to review this navigating Onshape thing. But anyway, highly suggest going through these. And if you want, we could sit in the class here for a little bit and everybody can start this navigating Onshape one. You can get familiar with the thing and let me know if you have any questions. And then next class, we're going to get into sketching, which is kind of the basis for all things you will design in CAD. To make something in 3D, you must first draw something in 2D in nearly every case. There's very few exceptions to that. So you're going to eventually need to get good at 2D sketching in order to get good at 3D modeling. So we're going to go into things like lines versus circles versus arcs versus parabolas, to different ways that things are related to each other, such as parallel, perpendicular, things you might have heard before, concentric, to things you may not have heard before, like coincident or tangent. Most people have heard the word tangent, but they don't always know what it means in the context of sketching. So that's where we're going next. I think that's the class for today. Does anybody have any questions or concerns or suggestions, anything along those lines? Perfect. All right. I'm going to leave it there, and I'll give you time tonight if you would like to continue to work through these tutorials. If you do get through these tutorials and you'd like to keep going, you could literally do any of the ones in this course catalog. I wish that they were done in like a specific order, because like the detailed drawings one is not the first one that I would suggest for people to take. And it doesn't seem like they have a specific order. Oh, you know what it might be? It might be under learning pathways. Yeah, you know what? It's learning pathways. So in that course catalog, if you go under learning pathways and you open CAD, this will be the one that brings you through each of them in the order in which it suggests you should take them. So you see this one, it has navigating Onshape, introduction to sketching, part design using part studios, multi-part studios, Onshape assemblies, and then detailed drawings. And that's the order in which I would generally teach these things. For example, you can't make a part drawing of something that you haven't modeled yet, and you can't make an assembly if you don't have a part yet, and you can't make a part if you don't have a sketch yet. So this is generally a really, really good order in which to continue. And you actually get these little certifications of your ability to use Onshape as you go through these self-learning modules here. So this is probably where I would go, Onshape fundamentals, and I will copy and paste that in the chat for everybody to use. Get as far along as you can. If you don't want to do them either, and you'd rather just like work along with the class, that's fine. I think these just give more information and more detailed information generally than what I give. This class is going to be how much you put into it is going to be exactly proportional to how much you get out of it. Just taking this class, you're not going to learn CAD. You're going to need to use it and practice it and do new things with it. I'm not going to be able to teach you every single scenario of how to design something, but I'm hoping that the class will give you the tools to be able to learn how to design something new. to give you the familiarity with CAD and the general concepts that you could take that knowledge and now design something awesome moving forward. Okay? Awesome. Any questions? Anything? Any comments? Emily, would you like to say anything?
Not really. Just if you have any questions, you should email either the FTC account or the 272 account. I know I sent some emails before on my personal, like, school account, but that's being shut down next month, so, I won't be able to, if you email me there, I won't be getting it. But, yeah, just have fun with it, I think. And I think if you get a good handle early on just the basics, then it will make the rest of the class a lot more fun, and you'll be able to understand what we're learning a lot more throughout the class as it goes on, and that'll just make the whole process a little bit smoother. So yeah.
Yep, perfect. Thank you, Emily. I agree completely with what she said. Have fun, mess around. At this point, you haven't made anything that you could break, so just dive right into it. If your best way of learning is just like play, maybe the best thing for you to do is just make a document, go in there and start making lines and seeing how things relate to each other. Maybe try to draw something that is interesting to you. Some of my like best learning experiences where I would literally just like pick something up from my desk like this. This is a little case for a microphone that I have. I would just pick it up and I'd be like, oh, can I model that? And I'd just go into CAD and try to model it. So just pick something up, see if you can make it real, and try that, or just take these tutorials. There's no right way to learn CAD. There's no wrong way to learn CAD. Just have at it. Have fun. All right. With that, I'll let all of you go into your learning here and have fun, and reach out to me or Emily if you have any questions, and I will see you all on Wednesday.
Thank you.
Perfect.
Have a good night.
Thanks,
Thank
Phil.
you. Yep.
Thank you.